So, well, welcome back, everybody, and I hope you all had a great weekend. And thanks again for excellent answers to the second midterm. Just wanted to quickly say something about the plans for this week. So this is our second last week, unfortunately. It's always sad when a semester comes towards an end. So we are going to look at this formalism of the calculus of variations and the Lagrangian formalism. And this is going to serve for many of you as a kind of stepping stone when you move on to more advanced physics courses. And we are also going to look at something which is called the principle of least action. So these are principles and mathematical formalism which you will encounter in many, many different circumstances. You may have seen some of it in mathematics courses. We will continue on this on Wednesday and for the rest of the semester. So we're going to look at this formalism, this Lagrangian formalism and principle of least action and variational calculations, or calculus as it's called. I also wanted to mention to you that this homework number 9, since you all were stressing with the midterm till the weekend, we decided just to push a little bit the deadline. So instead of having the deadline this coming Friday, because I guess you guys are pretty fed up of handing in these different assignments. So we just thought of having it next week. And there is also an additional assignment. So this is optional, but if you want to have an additional score, there's a possibility of gaining an additional score of 10%. Now, this specific assignment, which we have now, the first part is actually a repeat. The first 4 exercises is more about central forces and manipulations of orbits, just to convince yourself that you can get parabolic, hyperbolic orbits and so on. So it's essentially a paper and pencil exercise, set of exercises. And next Friday, not this one, then we will also make available the last final project. And that's going to look like more or less like the assignments and the midterms. But that's going to have a deadline by May 6th. Okay, so I wanted to just say something about this Lagrangian formalism. So one of the things which I mentioned last week was that we, in this calculus of variations, what we actually going to optimize. So when we say optimizing, it means to find the minimum or maximum of a specific function. So calculus of variations deals with you finding the minimum or maximum of something which can be represented by an integral. When we think of the work-energy theorem, that's actually something which is represented by an integral. And in physics, you will find many quantities which are given in terms of integrals. So when you integrate up the forces, you have the potential energy. And when you look at the work-energy theorem, you have the difference between the kinetic energy at an initial state and the final stage. Now, one of the things we said is that the quantity we want to integrate over, which we call the Lagrangian, is the difference between kinetic energy and potential energy. So it's not kinetic energy plus potential energy. And you may wonder why we take the difference between these two quantities. Why don't we calculate just the total energy and then look at the optimization of that one in order to find the equations of motions? So one of the things we did last Wednesday was to take this Lagrangian, and you saw that we could derive Newton's equation of motion. Now, calculus of variations is not something which is limited to physics. We are going to see that you can prove with calculus of variations that you can show that the optimal distance between 2 points is a straight line. So you can actually show that. So you're optimizing the path between 2 points. And in physics, in specific, if we have energy conserving forces, we know that the work which is done is independent of the path which we have taken. That's a very strong and important statement. So there are many small relations here. Now, what happens when we take the kinetic energy minus the potential energy is that we can derive Newton's equation. So one thing I should say is that also that when people introduced many of these things, they were actually playing around with kinetic energy plus minus potential energy. If you take plus the potential energy, you want to derive Newton's equations. But there's something more to the picture than meets the eye here. And I just wanted to show you something in order to build up the intuition why we define this Lagrangian as a difference between kinetic energy and potential energy. So let's take a short look at something which we did in the second midterm. So let me bring up the Jupyter notebook here, and we are going to take a close look at the conservation of energy, which we studied in the second midterm. So what you have here is a calculation of an elliptical orbit for the Earth-Sun case. You remember in this exercise 1E, we put the velocity to 5 in this kind of units with astronomical units divided by number of years. And then we got a elliptical orbit, and we saw that the total energy is conserved, whereas the kinetic energy and the potential energy, they would fluctuate because the radius itself would oscillate between a minimum and a maximum value. So if you look at this curve, think of this one, and now what you would like to, as a function of time, so this is a kind of a keyword to understand why we don't look at the kinetic energy when we want to optimize, no, the total energy, when we want to optimize this integral, but we look at the difference. If you look at the potential energy and the kinetic energy summed up, the total energy here, as a function of time, can we from that result here extract some kind of variations in velocity and position? No, it's just dead flat. So if I take in the circular motion, things would be a little bit boring. So the thing we want to see now is the difference in how the position and the velocities vary over time. And we want to optimize a quantity when we move from one time to a final time. And this is essentially what we end up with in this calculus of variations. If I now calculate the kinetic energy minus the potential energy, so this, in this case here, the total energy is just boring flat. There's no change. So if we wanted to look at the fluctuations in velocities and positions and try to optimize an integral in terms of these quantities, we wouldn't be able to extract much. If I, on the other hand, if I take and calculate the difference between kinetic energy and potential energy, you will see that the blue curve here, that shows to us the variation in velocity and in position. Now, the kind of machinery which I'm going to go through now is in principle independent of this specific physics problem. But what comes out in a very neat way is actually the equations of motion. You may not encounter cases in further physics courses where the Lagrangian is actually the kinetic energy minus the potential energy. But for classical, non-relativistic mechanics, this is the way we would define it. So what I'm going to do now, after this kind of motivation, or sort of motivation, we are going to go through the mathematics of the calculus of variations. And from that, we are going to derive something which are called the Euler-Lagrange equations, which are the equations we can use to find Newton's law. So that means that when we now move into more interesting cases or complicated cases, we can actually start with the kinetic and potential energy, and we can derive the equations of motions, which we then solve numerically and find the position and the velocity. So at the end, the thing which we are interested in is perhaps not the way the kinetic and potential energies vary, but how the position and the velocity vary as a function of time. And these are quantities which describe the dynamics of the system. However, in many cases, it's actually easier to start with kinetic energy because that's the same, irrespective of system. And then the only thing we need to sort out is the potential energy. So this formalism is also extremely powerful when we are looking at energy conserving forces. And we will see examples of this for the rest of the semester. And we're also going to look at what's called constrained motion. So you can add to this Lagrangian a constraint. So a constraint could be that you are sliding down a plane. If you add this constraint, that gives an addition to the Lagrangian, and you can derive the equation of motions with a constraint on top of it. And that's an extremely elegant way of formulating a physics problem. So let me try to step you through this kind of details. So we are just mainly going to do some whiteboard exercise today and go through the mathematics of variational calculus. So let's do that. So I'm just going to switch to the whiteboard. That. So as we mentioned last time, there are some basic ingredients. So one is the principle of least action, and then we have variational calculus. So let's just bring up these two elements. So there's a principle of least action. So what we are going to look at is actually the kind of path which brings us from one time to another time with the least difference between kinetic and potential energy. We know that if we look at the total energy, this is going to be flat if we, as a function of time, and you've seen that in the midterm. So if we then want to calculate the variation in a quantity, when we look at the total energy, that is just going to be a constant. So we won't gain much information from that. So we need a principle least action. And then there is something else which we are going to look at, and that's the calculus of variation, or what's normally called variational calculus. And these are some of the basic ingredients in this Lagrangian formalism. Now, the variational calculus, what does that deal with? So that deals with, let's just state that immediately. So that deals with finding the minimum with finding min or max, or the maximum of a quantity which can be expressed as an integral, which can be expressed and one of these quantities would be, for instance, to prove that the shortest distance between 2 points is a straight line. And we are going to see that a little bit later, to be expressed as an integral. And in physics, there are many quantities which we encounter which can be expressed as integrals, as an integral. And in our case, the quantity which we are going to define is a function s, which is normally called the action. So it has its own name. In mathematics, you may not find that. We just be defined as the variational integral. And we are now going to just introduce time as a variable. It doesn't need to be time. So we have a time t1 to time t2. And there is a quantity which I'm just going to call for L. And we're assuming that this is a one-dimensional quantity, and it's going to depend on the position of velocity, which is the derivative, and time. And this is integrated over time. So what we want to do now is actually to optimize this quantity as a function of time. So think of you doing some work from a time t1 to time t2, and you would like to optimize the path, which then minimizes the work which needs to be done to move, let's say, some object under the influence of some forces. So mathematically, what it stands for, the variational calculus, is you trying to minimize or maximize an integral. And remember now that if you think of the work energy theorem, we know that the work which we do is done by the integral over the force when you move an object from a position 1 to a position 2. And that could be done in a time 1 to a time 2. So let's just continue a little bit along these lines. So we want to optimize this quantity. And what we want to do is actually to define a function which now can move along a specific path. So suppose now that we start at a time t1, and remember this doesn't need to be time. So when we are going to look at the shortest distance between 2 points, we will not deal with time. So just keep in mind that this doesn't need to be time, but in our case, it suits well because we're looking at the dynamics of a system. And you could now think of being in a position x1, and then there's a position x2. Now, suppose now you start here, and you start there. Now you can there are many, many paths which lead to the final point. So let's assume now that this path which you see here is the optimal path. That's the one which minimizes that integral. So in a certain sense, this would be the quantity which minimizes the work which is needed to bring you from one point to another point. However, you could also think of taking many, many different types of paths. So suppose now that somebody tries to cheat you a little bit and tells you that this is the fastest or the best path, the red one, and then you want to have a way to evaluate which one is the path which brings you with the smallest effort to a specific endpoint. And that's why this is also called the principle of least action. So what you could think of now is the following. So if you look at the red line, you could now think that you have a function of x, which we don't know, plus some change. So let's call this an eta of t. So we make a perturbation to the path, which we're looking after, and we have the original path x. So let's call this is the optimal path. We just call that x of t. We don't know that. What we know is that there is a myriad of such paths, which you can take from t1 to t2. And you are now asking yourself, can I actually optimize this specific integral so that I actually take the best possible path, which for instance minimizes the energy which is needed to bring you from one point to another point. So this is a kind of overarching perspective I want you to have when we are thinking of this least action principle, which is then linked with variational calculus. So we are now going to look at variations, and the variations in the path are going to be given by this function eta. So we don't know these functions, but let's see if we can make some meaningful statements without knowing the values of this function or the functional form of these specific functions. So what we're going to say now is the following. So what we would like to is that when we make this change in path, there is a difference now, which we call delta S, which is a difference between x plus this eta minus S of x, where S of x is the optimal path. And we want to drive this one to 0. This is our ideal. So if we make such a change, we now want to find which is the path which minimizes this type of work which is done. Now, the thing which we're going to do first now is simply to assume that this function L, which we have defined, L of x, of the velocity and time, is actually given by the kinetic energy. So we're going to be specific now, and we're going to be in one dimension. So this is going to be dx dt. And we are going to assume now that we can simply take the difference between the kinetic and the potential energy. We can actually leave this open. So the thing which happens now when you move along different paths is that you will have variations in kinetic and in position and in velocities. Now we are looking after the path which minimizes the fluctuations in position and velocity by taking the difference between kinetic energy, which depends on the velocity, and the potential energy, which normally depends only on position. So we're already assuming now that we have a potential energy which depends only on the position. As I said, this kind of formalism is very much tailored to potentials which depend only on the position. And this leads normally to energy conserving forces. So let's just assume it. And you will see that when we're done with the mathematics here, if we take a minus, we're actually going to obtain Newton's equations. If we don't have a minus, we're going to have the acceleration is equal to minus the force. So when people looked at this type of formalism, they actually played around with whether we should have kinetic energy plus potential energy or kinetic energy minus potential energy. Now what comes next now is just a kind of manipulations. So it means that our function S is simply now going to be given by an integral from t1 to t2. And remember now that we don't know the value of x as a function of t. That's an unknown quantity. But we want to maximize this quantity here so that we get the optimal path, minus v of x. And this is an integral over time, dt here. So the quantity which we then want to look at, so this is what we would call S of x. And now we're going to look at this small change. So we're going to look at S of x plus eta, so the new path. And we assume that this eta is actually a quantity which depends on time only. Another thing we should say is that at eta, at t2 is equal to 0, because then there's no change. So we know the start point and we know the end point. So that means that this function at these two endpoints have to be equal to 0. So the function values have to be equal to 0 at the endpoints. Then, if I now plug in this variation here, I have an integral from t1 to t2. I have now the quantity 1/2, the mass, and now I need a derivative d dt. And now I'm making the change of x plus eta. And this quantity is squared. And then I have minus v of x plus eta. And then this is integrated over time. Now, the thing which I need to be a little bit careful with is obviously the quantity which I have, which is dx dt plus d eta dt. So I'm going to do some manipulations now. And we want to square these quantities. So if we square it, so this is essentially what we have in here. So this equation here. So we're going to square that one. So that gives us d of x dt squared plus a d of eta dt squared. And then we have plus 2 of d of x dt of d eta dt. So there are some manipulations which we are going to need now. Furthermore, we are going to look at the perturbation around x for the potential energy. So if we do a Taylor expansion, this is going to be v of x plus eta times the derivative dv dx plus eta squared divided by 2. And then we have the second derivative. I'm just going to write it like two dots up here, plus the higher order terms in terms of eta. Now, one of the things we are going to do now is simply to ignore higher order terms. Sorry for that. Just even if it's snowing outside, the allergy always kicks in. So April is the classical allergy month. Okay, so what we are going to do then is that we will ignore these higher order terms in eta. So we ignore these. And then we look at the changes to first order. So this is the basis for variational calculus. We are assuming now that the higher order terms, they can be neglected. So we are just going to look at the change to first order in eta. And this follows also from what we did when we developed the potential for the harmonic oscillator. So when we looked at the harmonic oscillator, we were looking just at small oscillations around the equilibrium point. So at the bottom of the potential well, we have a first derivative, which is 0. And then we simply stop then at second order terms, which were second derivatives. And from that, we could derive a potential for the harmonic oscillator case. So what we are going to do now is to take the difference between these two terms, and we are simply going to keep terms which are to first order in eta. So that means that our term here, this Sx plus eta, is going to be given by 1/2, not T1 to T2, and then we have 1/2 multiplied with the mass. So this is a kinetic energy term. It's going to have a dx dt squared. And then we have the term which goes like S of x. So this is plus dt. And then we have the other terms which come in like plus T1 of T2. And then I have 1/2 times m. And this is now multiplied with 2 of dx of dt of d eta dt minus, and then we have the correction which comes from the potential energy of dv dx. This is multiplied with dt. So this is S of x, and then we skip higher order terms in eta. In this eta. So we should in principle put an approximation sign here. Then, when we now take the difference between this term x plus eta minus S of x, and we want to drive this to 0. So this is a quantity we now want to optimize. And if we do that, if we take the difference here, what we end up with is just an integral from T1 to T2. And then we have 1/2 the mass of the particle. We have a multiply with 2 dx dt. And we have a d eta dt. And this is minus an eta times dv dx. And this is finally multiplied with dt. Now the thing is that x of t is actually unknown, so we don't know that one. And we would like to get rid of this term, and we want to get rid of, because we don't know that term either, to get rid of this term which we call d eta dt here. So what comes now is a new mathematical manipulation. So what you see is now the difference where we have only kept terms of first order. So when you're looking at variational calculus, the whole premise for variational calculus is that these high order terms are negligible. So we're just looking at the difference between the first order perturbations to the path. Then what we need now is just a small trick. So we need to get rid of this term which goes like d eta dt. In order to do that, we are going to simply put in dx dt. We're going to look at how we define this one. So when we write it out, this is going to be given by dx dt. And then we have d eta dt plus, and now we have the second derivative. So this is just the standard derivation rules, dt times eta. So there's nothing new here. So if we now look at this term which we want to get rid of, this dx dt, d eta dt, we can actually rewrite that as this d dt of dx dt times eta minus the second derivative here, d of x dt squared, on dt, the second derivative of x with respect to time. So if we now go back to the equation which we had, the thing which we are going to do now is to replace the term you see here with the definition which we ended up with here by just manipulating the derivatives. And what's going to happen then is that we can then isolate the derivative with respect to x squared and reinterpret that in terms of a kinetic energy multiplied with a specific term. So let's take a look at that. So we bake it back into the integral. So if we now take the integral which may cause some problems, or the one where we want to get rid of the term with dx dt multiplied with d eta dt. So this is something which we now can rewrite in terms of this t1 of t2, and then we have d dt, and then we have a dx of dt times eta multiplied with dt, and this is minus, and then we have a term which goes like t1 of t2 of d second derivative of x with respect to time multiplied with eta of dt. Now, if you look at the first term, which we have, this is pretty easy to integrate because that means that what we get when we integrate that one, we get simply dx dt times eta, and then we have the time limits from t1 to t2. Dx dt, we are assuming it doesn't diverge at these endpoints, but we have defined the function eta at t1 to t2. So this specific function which you see here, we have defined that one to be 0 at the two endpoints, because then we have no perturbation of the path, because we know the value at the endpoints, which means that the first term here just vanishes. So that one disappears. So we can put this one to 0, because eta of t1 is equal to eta of t2. We have no variation at the two endpoints. We know the values of the endpoints, but else we don't know the value of x. And then we have minus, and then we have an integral of t1 of t2 of d second derivative dt of eta times dt. Now, this term which you see here is actually quite interesting. So this specific term, the second derivative with x of dt, what's that actually for us in mechanics? So it has a famous name. And it begins with the first letter in the alphabet. Yeah, the acceleration, exactly. So this is actually an acceleration. So we are going to see now that we are going to get an equation where we get Newton's equation when we require that the change in this action, which we called, due to the change in path, is going to be give us Newton's equation of motion. And that's pretty neat. So let's see that. Let's try to see that and convince ourselves that this is actually the case. So when we now plug in things, what we have is a following integral. So we want this delta S to be equal to 0. And that's the same as us requiring that T1, the integral from T1 to T2, so this is now given by this minus m. We got rid of the factor of 2. We have the acceleration here. And when we see the expression which we have here, this actually looks like our force, but with a negative sign. It's multiplied with this eta. And then we have minus dv dx multiplied with eta, and then integrated over dt. Now, we are assuming that eta, except for the endpoints, is different from 0, because else there wouldn't be a change in the path we are taking, right? So if eta was 0 all the time, then there wouldn't be a change in the path. So now we're actually optimizing with respect to this eta to find what minimizes the action which is needed to bring you from one point to another point. So if you now look at the equation here, what this means is that we have to require simply that we have T1, T2, and then we can put eta outside, m d second derivative with respect to x, dt minus dv d of x times eta multiplied with dt. And since we assume now that this eta, except for the endpoints, is equal to 0, this simply means that we have to require that m of d second derivative, and this is something we can generalize to higher dimensions, is equal to minus dv d of x, and that's simply the force. And in our case, this is actually Newton's law in one dimension. So we have actually, by starting with this difference between kinetic energy and potential energy, and requiring that the fluctuation in velocities and position are so that we minimize the path when moving from one point to another one, this is a very powerful way of finding Newton's equation. And you see now that if we hadn't taken kinetic energy minus potential energy, we would actually have gotten a plus sign here, and that means that we would have had that the acceleration is equal to the negative force. And that is not exactly what we have defined as Newton's law. Now, when you are going to do quantum mechanics, you can actually derive Schrödinger's equation from potential energy and kinetic energy. So this kind of formalism is extremely powerful. So it's not something you would only use in mechanics, but you can apply it to many, many other different fields of physics. So it's a way where you can derive equations of motions starting with kinetic energy and potential energy. Now, the thing which I haven't given you now, so we did this demonstration for an explicit case, and we got Newton's equation. And you see now that putting the difference between kinetic and potential energy actually gives us Newton's law. But let's now generalize this so that we can have a general equations which are called the Euler-Lagrange equations. So that means that if you have the Lagrangian and you implement these equations, Newton's law should pop out immediately. So it's an extremely elegant and powerful formalism which is based on the principle of variations, or variational calculus, where you actually are optimizing an integral so that the difference you take from going from one point to another one is optimized, either maximized or minimized. So you can have a minimization problem or a maximization problem. Often in physics, we end up with minimization problems because we are looking at the minimum often of the energy. And that's normally a convex function in physics. Okay, so let's now bring in the final element which we need in order to derive these equations. So keep also in mind that we have skipped higher order corrections in this perturbation of the path. So the thing which we need now is this next ingredient, which is to generalize everything in order to have a set of equations which we can simply plug in and derive the equations of motions without making specific assumptions here about the way we calculate the integral, as we did now. So what we want is to generalize this, and we are still going to start with L, which we just call a general function of x, v, and t. This is a pretty common situation in physics. We are going to look at changes in position. So we're going to call these changes in position. So this is the same as our eta, which we had before. So this was this eta of t. And then we are also going to look at a change in velocity, because this is the other variable which changes with time. So it's not only the position which changes, and we are going to look at how we can optimize the change in energy when velocity and positions vary and change, as you have seen in the second midterm. We had oscillations in kinetic energy and potential energy, but the total energy was a constant. So what we're also going to require now is, if we make this plot again, where we are moving from a position x1 at a time t1, and we end in a position x2 at a time t2, we are going to assume again that delta x, sorry, not that way, but this way. So delta x of t1 is going to be equal to delta x of t2, which is 0. So we have an ideal path, which I mark with blue. And then we make these changes here. So we have this path, which is perhaps less ideal. And that's going to represent our change in the path. And in the two extreme points, we know the value of the function x. And then we have no variation, because that point is fixed. And then we also have a delta v of t1 is going to be equal to a delta v of t2. And these are also going to be 0. So if we then, what we're going to do now is to use partial derivatives. And we have x plus a delta x. And we have a v plus a delta v as a function of time. And this is going to be given by L of x, v of t, plus, and then I have the first derivative with respect to x. And I guess you've seen some of these equations here in mathematics courses. So I hope this doesn't come out as a bolt out of the blue. And then we have a dv of d, sorry, not delta x, not dx, but delta x. So like this, delta x. And this is the change in velocity, delta v. And then we have a term which goes like plus higher order terms of delta x squared plus O of delta v squared. And then we have also neglected a cross term between x and v. So there are cross terms to higher order, which go like delta v times delta x. So we are going to neglect these terms, so that at the end, we are just going to have an equation which is going to contain these three first terms here. So we are going to neglect higher order fluctuations in the path which we take, as we did in the previous case. So when we then calculate this difference, so what we need then, we want to optimize this action, as it's called, which is the difference between the integral over L of x plus delta x of v plus delta v of t multiplied with dt minus the integral over L. So this is essentially what we did in the previous case, except that in the previous case, we manipulated in particular the position itself. Now we want to generalize this so we can also change the velocities. So what this means is the following. When we now put it up and we plug in the equation which we have up here, you will see that the first term is going to cancel the second term here. And then we are simply left with these two terms here. So what we are going to get then is an integral which we want to optimize. And this is going to be given by a first derivative with respect to x for this delta x, plus this partial derivative of the Lagrangian, or this function we are looking at, as a function of the v. And this is multiplied with dt. And we want to drive this quantity to 0. Now, this quantity here is actually something which we can write out now in terms of a delta L, delta V, and we know that this is the derivative of delta x. So this must be d dt of delta x, because that's the change in position. So this change in velocity must be given by the change in this delta x as a function of time. That means that what we get then is the following. So if you look at these equations, which we have, and we take this specific term, which we have put out here, this one, we are going to get something which, when we do integration by parts, so I integrate by parts, this is essentially what we end up doing here. We are going to have a delta S by integration by parts, which is given by delta L of delta V, and then we have a delta X taken from the limits of T1 to T2, and we know that this quantity here is actually equal to 0 at these limits, plus an additional integral, which is simply T1 to T2, and then we are going to have a delta L, delta X minus, and then we have a d dt of dl dv, and this is multiplied with, again, with delta x multiplied with dt. So what we know is that at delta x at t1 and t2 is equal to 0. T1 is equal to delta x at t2, and that's equal to 0. So that means that if delta x is arbitrary anywhere else, it means that we get an equation here which has to be fulfilled. Delta x, the derivative with respect to x, and the time derivative of the partial derivative with respect to the velocity of dv, that has to be equal to 0. And these equations here are called the Euler-Lagrange equations. So these are the Euler-Lagrange equation. And if you're just in one dimension, we have two equations, one for x and one for v. If we go to more dimensions, we would have a similar one for y, the velocity in the y direction. If we have the z direction, it's z, and the velocity in the z directions, and so forth. So this is a famous equation in the calculus of variation. If we apply this, as we saw in the examples which we had last Wednesday, we could derive Newton's law from these equations here by defining a function which is given by the difference of kinetic energy and potential energy. And that's extremely powerful because we can generalize this to other types of coordinates as well. And we are going to see several examples of this now. So, but the first example we're going to look at, and we will pick this up on Wednesday, is the shortest distance between 2 points. So this is going to be our first example. So that's shortest distance between 2 points. So we can use this calculus of variations to simply demonstrate that the shortest distance between 2 points is what everybody knows, a straight line. But I see my time is running out. And since I've often been stealing 1 or 2 minutes extra, I'm going to stop 1 minute before. But I'm not going to let that develop into a habit. So, yes. Okay, guys. Thanks for coming. So we're going to stop here, and then we keep on with this formalism with examples through the rest of the semester. Okay. Feel free to hang around if you have questions. Never hesitate to ask questions. So